My name is Fernando Camizani. I'll be your chair for this session. I'd like to welcome you to this plenary session entitled Large Transport Aircraft, Control Challenges of the Future by Professor Thomas Jones. There are two sessions happening in parallel. The other one is in Auditorium 1 on power systems. Interestingly enough, the two presenters, that is Professor Jones and Dr. Schultz, happen to have been students together at MIT, and they are South Africans, and now they're presenting at the same time. Unfortunately, we couldn't schedule it that they were after each other, but I'm pretty sure you will enjoy this session. I'll give you a short biography of Professor Jones. After receiving his Eng and MSc Eng degrees in electrical and electronic engineering from Stellenbosch University here in South Africa, Professor Jones started his career at Aerotech, which is a division of the Council for Scientific and Industrial Research, as well as Stellenbosch University as a missile navigation and guidance system analyst. He relocated to the USA to first join the MIT Artificial Intelligence Lab and then the Draper MIT Technology Development Partnership Program, and was appointed as manager of the development program while completing his PhD at MIT's Department of Aeronautics and Astronautics. He has more than 15 years of experience designing and building innovative practical solutions to aerospace control challenges on aircraft and missiles of various sizes, types and configurations. Professor Jones currently serves as head of the Department of Electrical and Electronic Engineering at Stellenbosch University, and in his research capacity he leads a team of 30 graduate students and academic staff specializing in aircraft and unmanned system automation. He has forged strong research partnerships with many local and international organizations, including Airbus, the Armaments Corporation of South Africa, Denel, the CSIR, the National Aerospace Center, and local and international universities. In 2008, he co-founded S-Plane Automation, a company successfully specializing in the development of high-end aircraft avionics and automation subsystems serving the international market. Professor Jones is inter alia a member of Ifac's Technical Committee on Aerospace, an associate editor of Control Engineering Practice, and a member of the Executive Committee of the South African Council for Automation and Control, which is the Ifac NMO. I'd like to ask you to enjoy this plenary very much, and I'd like Professor Jones to take the lectern. Thank you very much.
Good evening, everyone. Got the light in my face, I can't quite see you, but I'm sure you can see me from back there. Thank you for taking time out in your evening to listen to my presentation this evening. It is an honor to be here, and I'm delighted to be able to present this work to you. My title of my work, of course, right up there, Large Transport Aircraft, Solving the Control Challenges of the Future. I'll give you a quick introduction so you can decide to go to the power systems presentation or not in one slide. We're really pretty much talking about industry and academia collaboration. And you've seen today that there were a number of discussions on the matter. First this morning with David Voss's plenary, where he talked about all the different requirements for automation and systems engineering, all the challenges that we're looking at in the aircraft sector. We listened to a special panel and took part in a special panel discussion, in fact 2 special panel discussions today talking about industry and funding and relevance and so on. And on Thursday afternoon around 4 o'clock there's a special invited session organized by Andres Marcos of University of Bristol and Philippe Gopel of Airbus, also specifically on the successes and the processes of industry and academia interaction. So I suggest that you also take some time to go and see that session. What I'm trying to demonstrate here today is essentially a success story, and I'm going to move slightly to the side where there's less light in my face. Today is really about a success story. So it's trying to show what we can do when we collaborate with industry. The kind of industry that we're in terms of large commercial transport aircraft, it's difficult to do a lot of flight testing and these sorts of things, so you'll see very much a focus on simulation, but with high fidelity models. But at least we can show that the sorts of things that we're working on have relevance. I'll show you some focus areas to give you a good idea of what it is that we're looking at inside the field of automation and control for large transport aircraft. And inside those focus areas, I'll show you some of the example projects that we've been working on together with Airbus and the National Aerospace Centre. And the research approach, given that we're really talking about working with industry and having industry relevance, is pretty much to have practical and realizable solutions that we can implement in industry environments. David Voss this morning talked about hundreds of dollars per line of code to get these lines of code certified to fly an aircraft. So we need to reduce the numbers of lines of code. I mean, try to draw from everything that we already have in existence, and we're not trying to reinvent everything as we go along. All right, so I'll give you some quick context of who we are. We'll talk about what we do, and then I'll jump right into the focus on large transport aircraft. And you'll see three themes throughout the presentation. Firstly, general functional automation. It's one of the things we'll be looking at, improving safety and improving efficiency. And I'm going to show you some examples falling within those categories, and I'll elaborate on those categories as I go along. And towards the end, we'll have some quick conclusions. So just to put everything in context, I'm from Stellenbosch University. So in the South African context, we are a pretty old university, founded in 1886, about 60 kilometers east-northeast of here. So an half an hour drive or 40-minute drive for me to get here. It's a comprehensive university. Like most comprehensive universities, we have a few campuses. We have 10 or so different faculties, 28,000, 30,000 students, depending on when you count. And according to the National Research Foundation in South Africa, we are pretty much the most effective research institution in terms of outputs in South Africa per member of staff. So we put out quite a number of publication units per senior lecturer equivalent, it's called. So if you look around different kinds of ratings for universities, we're in the top 200 or so. We're not MIT, we're not Stanford, we're not Caltech, but we're a pretty solid university in the world arena. I'm inside the Faculty of Engineering at Electrical and Electronic Engineering. We have about 650 or 700 students, and the entire faculty, we have about 4,000 students or so. Now, inside the Department of Electrical and Electronic Engineering, delving deeper into where we are, we have the Electronic Systems Laboratory, the lab where I do my research, together with my colleagues. It was originally founded in the early 90s as a space systems laboratory after the satellite and launch vehicle programs of South Africa came to an end in the 80s. We have about 50 or so graduate students in total, and maybe 12 or so academics also, depending on when you count and how you count. Our research focus is really on automation and control. And in the broader sense of automation and control, we do everything from robotics and automation and control on one end, and path planning and collision avoidance, all the way through to linear matrix inequalities and robust control and anything else that we need along the way. We do some general work on lasers, pulsed, solid-state lasers and so on, but all the way through to our main focus is really on space vehicles, terrestrial vehicles, underwater vehicles, and aircraft. And today, the discussion is on aircraft. When we talk about aircraft, we have an unmanned aircraft side to what we do, and I was lucky enough to present a plenary in India earlier this year on some of our work in that arena. I'll keep that for another day. But we're here to talk about large transport aircraft and the automation work we do for large transport aircraft and how it works in our collaboration with industry and so on. Firstly, it's important to understand how it all works. In about 2008, an Airbus researcher and employee, Etienne Coetzee, spent 6 to 8 months with us in our laboratory on a secondment. And during that time, we figured out that we have a whole lot of work ethics and issues and focuses in common, foci in common with Airbus. And at the time, we started a program sponsored by Airbus Central Entity, where we had exposure to centers of competence at Airbus, and we would work with those centres of competence. Specifically, it started in Toulouse and in Bristol or in Fulton, to solve interesting future challenges in the aviation sector and the large transport aircraft sector. Specifically, the challenges aimed, say, 5 to 10 years into the future, or even 15 years into the future. Not in the next aircraft, but maybe 1 or 2 aircraft down the line. It was quite successful right from the start. We first expanded to 4 or so other universities, and shortly after, the next few years, we expanded to all South African universities on a merit-based system. So projects can now be defined on a merit-based process. So they are evaluated on a merit-based system. How it basically works is the Airbus central entity provides funding for us to start off working with centres of competence, and Airbus central entity provides half of the funding, and the South African Department of Trade and Industry, through something called the National Aerospace Centre, provides the other half of the funding. So there's some South African government sponsorship. We then work with those centres of competence, and as we go along, if our projects have relevance, if they're useful to those centres of competence, then we're weaned off the central entity funding, and we start working directly and being funded directly by the centres of competence. So I think it's a great model. If what you're doing is useful for industry, then industry and the specific part of industry that you're working with, they end up funding what you are doing. At the moment, we, in our electronic systems lab, are working with Airbus centres of competence in 3 countries, in Bremen in Germany, in Toulouse in France, and in Bristol or Fulton in the UK. And our niche remains automation and control, while many of the other projects in South Africa are of a wide variety, for example, titanium beneficiation, and lots of other interesting things as well. All right. To be able to work in this sector, you need to roughly understand the motivations. There's a lot more to it, but I'll try to summarize in one slide. If you look broadly at the development of large transport aircraft, the 3 main drivers, as we see it, would be to look at the reduction of cost, improving passenger safety and comfort altogether, and environmental impact. And this is pretty much what you see across the board in FAA statements at Airbus, at Boeing, and any other manufacturer. These are the main drivers that we see today. There are many other drivers, many other specifics in specific markets and specific products and so on, but these are the main drivers. We also have to understand the industrial environment, and David Voss pointed out many of these things this morning as well. We're dealing here with huge multinational organizations that are highly competitive with each other in terms of creating these large transport aircraft. And we work in a very highly regulated environment where certification really is a driving factor in whatever is done. If you do not take certification into account in what you do right from the start, then projects are made or broken right from the start. You need to understand what the impact of certification and regulations and so on will be. So again, I come back to our specific focus that leads in from what you've seen at the top here, from these development drivers and industrial environment. We look at general functional automation of aircraft, improving safety of aircraft, and improving efficiency through automation and control. And I'll handle each one of these quickly separately, and then give you an example, a project of each one of these that we're involved in at the moment. All right, so let's start with general functional automation. Pretty much adding useful operational automation features to aircraft that make aircraft nicer to fly or to fly in. We have strong links to safety and efficiency. If you take some of the workload away from pilots through automation and so on, then there are lots of things that you can do with that workload. You can reduce the workload on the pilot, and that's a very good thing. In the field of general functional automation, we have one of our example projects in that area would be automated airborne refueling, or AAR as we refer to it. And in this sense, we are talking about automated airborne refueling of transport aircraft. So you have a large vehicle refueling another large vehicle. So that's quite different from what you'd usually see with a small vehicle at the back as the receiver and a large vehicle on the front. Many reasons for doing this. Range extension without landing, for one, sometimes military environments, sometimes in civil environments, and larger cargo components as part of the total takeoff mass. You don't need to take off so much fuel. Maybe at some later stage you add some fuel to the aircraft. This is a difficult and strenuous piloting exercise, and I'll show you roughly why that is. So the first thing to understand about autonomous refueling as an example project of general functional automation is that because you have such a huge aircraft at the back here, refueling from one at the front, you have about, say, 83 tons of fuel if you take an Airbus A330 as an example, 83 tons of fuel to transfer. We've got to go for solid booming, so you have a solid boom that connects these two aircraft because you've got to transfer roughly 83 liters of fuel a second. So that's an SUV's fuel every second to do this job in 20 minutes. So you've got to go for a large, a fast transfer rate. So we're talking about solid booming. It's important to note that the receptacle, the receiver receptacle in this case, is behind the cockpit and above the cockpit. So the pilot doesn't really see the point where the connection happens. And that receiver receptacle is also way in front of the CG. Not like a small little aircraft where the CG is quite close. In this case, there are tens of meters between the CG and the receiver receptacle. And that makes a huge difference when the pilot tries to operate and regulate that receptacle. Whenever you pitch or yaw, you can see that the receiver point moves around quite a lot. So it gives you an idea of roughly what we're dealing with. In this case, in a KC-135 and a C-17 being refueled. So you have a booming operator, and the booming operator pops the boom right into the right spot, the refueling receptacle above and behind the cockpit there. And that can only be done if the aircraft, the trailing aircraft, is regulated to the correct spot so that the boom can reach. And that is the next problem. So let's have a quick look at what this looks like. You need to regulate the receptacle inside a very small area. And to make a long story short, that area is about 4 meters, it's a 4 meter cube. So if I lie with my feet in the middle of the box, my head is at the end of the box. That's it. So that's the amount of space you have in which to keep the regulation of that refueling receptacle. And for a large aircraft with all these constraints on where the CG is relative to that point, relative sluggishness compared to very small aircraft, that's a very difficult thing for a pilot to do, and even for an automation system to try to do. All right, so that's really the challenge, to keep the aircraft inside that little box. Not the aircraft, the refueling receptacle inside that box. All right, so let's talk about some of the goals. We want to do autonomous receptacle regulation. That's very clear. We want to do this under light and medium turbulence conditions, for example. That's typically when you want to be able to refuel. We don't want to mess around with the front aircraft. The tanker might be of different manufacture. It might be various complications, but quite frankly, you don't want to change a line of code on the tanker. You don't want to change much on the tanker, because as soon as you do, you've got to recertify what you do there. So our focus lies in trying to make changes to the trailing aircraft to provide an aircraft that has this functionality to keep station relative to a tanker. So in general, we try to keep the changes to a minimum. We also, along the same lines of keeping changes to a minimum, want to operate via the fly-by-wire system, because fly-by-wire systems have lots of protection inside for mechanical modes on the aircraft, for overloading the aircraft structure, and for keeping the aircraft in its flight envelope, all those sorts of interesting things. So we don't want to create something new there. We want to use what we already have in place. And lastly, of course, we need a high-fidelity model. We need to create a high-fidelity model or adapt models to be high-fidelity for this specific task, so that we can trust what it is that we are doing. And that's the next part, trusting what we're doing through improved modeling, and then trusting what it is that we learn from that improved modeling process. And then the next two steps basically come down to, firstly, saying, well, okay, so if we can trust this model and we know how the vehicles will behave relative to each other, then we can first try an insightful conventional design. We can first try to feedback a number of interesting variables that we can identify for the specific job, and we can see what it is that we can and can't do in that way as a benchmark, as a basic test. And then what we can do on top of that is to do optimal robust design, for example, to explore the limits, and even switch off the fly-by-wire system and explore the limits of what we really can do with these aircraft in some optimal way. All right, so let's see what we're doing there. Improving modeling, I can run through this quite quickly. Firstly, we can't deal with modeling around the CG, so we need to model around the receptacle position, so we add some zeros to the system. We had to look at the thrust models for this kind of system, because if you're going to be doing accurate longitudinal control, thrust is probably the place we need very good models. The most sluggish actuator on your aircraft will be your thrust. So there we looked at step responses on the specific motors used on the specific aircraft and model that we used, or the specific engines. and fitted some models there. And then lastly, proximity is another important part of what it is that we need to take into account. Firstly, proximity from the tanker, the effects of the tanker on the receiver aircraft. And there's a lot of literature about how to do this, although it's not always easy to filter out what is applicable for a large aircraft on the trailing side. But the most interesting additional part is the receiver effects on the tanker. And most people don't think of these effects initially, but in flight testing you see it quite clearly. The tanker has the receiver has a bow wave, and the bow wave at this kind of proximity that you see over here starts affecting the tanker. You push the tanker forward, you make it pitch forward as you approach. So it causes a bit of trouble. So we've got to be careful there. And initially, if you don't want to be messing around with control systems on the tanker, you've got to enforce some form of time scale separation, do something interesting there, and try your best to break the interaction between these two aircraft. Another way to break the interaction is to keep a simple control system on the aircraft on the front. So don't, for example, control the airspeed of that aircraft. Rather go to a constant throttle setting, a trim throttle setting, and approach slowly from the back of the aircraft. Right, so we do what we can to ensure that we don't mess around with that aircraft on the front. All right, so first we start off with a basic conventional design. So we try to see if we can just look at the longitudinal model for now. I'll present the longitudinal model here today. We also worked on the lateral model, of course. Some simple things we can do: classical control, LQR, basic feedback loops. We can try to cancel out some of these nasty zeros that ended up from moving our point of interest from the CG to the receiver receptacle. And we do, of course, need to know we can't cancel them perfectly. This is an industry project, so we need to know that we're going to apply imperfect pole zero cancellation, and we're going to see what those effects are, and we analyze what those effects are. On the actuator side, typically throttles and elevators, low bandwidth and high bandwidth controllers, but we also, under specific flight conditions for refueling, can add spoilers. Now, spoilers are air brakes. Some of you know them as air brakes. You basically have hydraulically actuated air brakes or spoilers. They're medium bandwidth devices, but to be able to use them effectively, it's a good idea to deflect them to a small deflection angle and then move back and forth from that point. So you can create, you have motion in both directions. So you have to retrim the trailing aircraft or the receiver aircraft to be able to do this very carefully before you approach the tanker. And like I said, basic control that we can attempt, and then we can see what we can do with some basic control. So this is just insightful, analyze, try to understand, and through understanding, try to create a control system. What you see here is a lateral view of the receptacle position. That's the blue bit. So you look at it from the side. Inside what we call the disconnect envelope is this red box. We have to stay inside. So the blue bit stays inside the green bit and is way inside the red bit. So we're pretty much regulating correctly under medium turbulence conditions in this case. And this is also straight and level flight. Laterally, it's not so great, but we do not fall outside of the red envelope, and this is typical of hundreds, in fact 1,500 or so simulations that we did at Airbus with one of our PhD students who also spent time there doing his internship. So we learn a few things from it. It is indeed possible to control in an automated fashion and regulate this receptacle inside the space, but there are a few things that we need to know. Firstly, we're regulating the receiver point. So if you're regulating the receiver point, you've got to understand that the CG is going to be moving around to do that. So your load factor on your aircraft increases quite a bit. And if you have passengers on board, they might not be as comfortable as they would normally be, especially under medium turbulence conditions. And I'll show you what that looks like soon. And generally, like I said before, try to keep the tanker control as simple as possible. That's when we get the best performance. Trim it, leave it there. Don't try to control it too much. If you try to push it back and forth to hold to specific velocities and so on, then the interactions start coupling more and more, and we start getting nasty effects between them. All right, so that gives us a first benchmark. We have an idea of what we can do if we just play around with some insightful control. Let's go a little bit further. Let's do optimal robust design. Now, in literature, you'll find that mainly if you look at this kind of problem, refueling in literature, airborne refueling, you can see it's been published before. It's mainly for smaller receiver aircraft. Actuation limits aren't normally included in these sorts of designs, and control accuracy requirements are normally not a part or an adjustable part of the optimizations. We also want to try to maintain the model complexity as much as possible inside this design, because we want to be able to come up with an answer to tell us what, as far as possible, the real limits of capability would be. In this case, if we, for example, don't make use of the fly-by-wire system. And I should point out with the classical type control that we do with the LQR control we did in the earlier slides, we still fly through fly-by-wire, and that's very important. All right, so our approach was to use linear matrix inequality optimization. Those of you who don't do this every day, we basically take the problem, we formulate closed loop stability and performance as LMIs. We then absorb a bunch of control variables into those LMI structures as part of the process. We remove all the resulting nonlinearities with lots of substitutions and transformations and shaping and all sorts of interesting things. We then define some objective function that we're going to be optimizing, and then you go out and choose the best optimizer to solve, and you solve that objective function, or optimize that objective function. So this is typical in LMI optimization. Now, the model we end up with is about a 60th order norm-bounded state space model. Now, for the aviation industry, that's quite a high order model. For process control and power systems, maybe that's not so much. Maybe you do thousands of orders, but in this case, about a 60th order system. All right. In keeping with trying to keep it as simple as possible, we don't want to add lots of additional sensors and so on to this aircraft, so we use what's called an output feedback model. It's a pretty standard way of putting all of this together. Output feedback model that we're going to be optimizing. We choose 9 different controller variants, depending on what sensor combinations we think we can and can't get, what kind of control feedback we can and can't get. I won't go into all the detail of that. And of course, we bypass fly-by-wire here because we want to see what is possible and see if we can optimize into a corner and get some good idea of what we can and can't do. And then we use, in this case, STPT3 inside MATLAB as our optimization engine. Okay, and this is what the result looks like. Much better, about improvement of 3 to 4 times on the standard deviation. So we can keep the receptacle inside a very, very narrow envelope. And that's the connect envelope that you see in the middle there, and the disconnect envelope on the outside there. So even if, well, this may or may not be feasible, we don't quite know because we've taken out fly-by-wire and so on, but at least what we should be able to say is that by insightful control with basic classical and state space methods, we can stay inside the disconnect box, and through optimization, we can do about maybe 3, sometimes 4 times better. So probably your answer lies somewhere in between there, and we do this for a range of flight conditions, not just for, say, 10,000 or 20,000 feet, a range of different conditions where we operate the aircraft. All right. So it gives you an idea of what we've been up to in automated airborne refueling, and it's worth just looking at a quick video. If you can start the video, please. Thank you. All right, so this is with not with LMI optimization. This is just an insightful conventional methods of control. You see the aircraft at the rear, connected the one at the front with a boom, and the important thing is not how these move for now, but that boom extension doesn't exceed the requirements. So we're in light turbulence. Here we're entering a turn in light turbulence because we need to be able to fly racetracks, we need to fly toboggan maneuvers, we need to fly straight line, we need to fly into turns, we need to come out of turns, we need to be able to show that we can regulate that receptacle. And in this case, all in light turbulence conditions. I also show roughly what it looks like from the perspective of the pilot to show you if you would enter into a turn, if you did this as a pilot, what you would need to do. Your reference points are really few. It's very difficult to keep the aircraft there. And remember, as the front aircraft turns and the rear aircraft turns, one's tail moves out and one's nose comes in, so it's actually quite a difficult thing to be doing. And of course, at the same time, you need to be exiting the turn and keeping the aircraft under control on that exit and keep the receiver receptacle within the bounds that are required. And this is, in fact, all doable. Now, this is what medium turbulence looks like. This is why I'm saying have a careful look at that. This aircraft at the back, it's trying to regulate that receiver, and it can do the job to keep this boom extended to its correct extents. But that aircraft at the back is moving a whole lot more. The CG is moving a lot more, trying to keep that receiver receptacle in place. So that's quite an interesting result. All right. So that gives you an idea, a project on general functional automation, roughly what it looks like, how it works, and some of the results that we've been able to achieve so far. Let's move on to something else. Let's look at improving safety. So, of course, improving safety and efficiency and general functional automation, those are the three areas we're looking at. Next is safety. Of course, it's a primary driver. Lucky for us all, we all flew here today and you got here safely, so that's a good thing. So it's a good thing that the industry always tries to improve. And there have been huge improvements over the past 100 years. Flight has never been as safe as it is right now, but still, it's never safe enough. We always try to improve. And always the first step of what we try to do is we try to ensure that our aircraft are protected from exiting envelopes. So we try to keep our aircraft within their flight envelopes. And this is the specific work that I'm going to be talking about, automatic return to envelope function. So let's, for example, say your aircraft is for some reason perturbed outside of envelope. Maybe there's pilot error, maybe there's some atmospheric conditions, maybe there are failures that cannot be accounted for, and this aircraft is pushed outside of its standard flight envelope. Like I said, mainly it doesn't go there, but if it does, our focus on this project is to push it back into the flight envelope in some automated way. And again, David Voss talked about that this morning. It ties in exactly with what he was saying in terms of the things we can do with automation, and to allow us to do these things with automation, we can do a lot more than we currently are doing. So automatic return to envelope functions. First, let's quickly talk about the envelopes. We define them in many, many different ways, but typically have something like load factor or acceleration and normalized airspeed. So you have a little box, and the aircraft shouldn't exit that box. You can look at normalized side slip angle and some normalized angle of attack and keep the aircraft within that box. You can look at bank angle and pitch angle, and you can say, well, okay, keep the aircraft within that box. If the aircraft exits that box, we refer to this as an exit from the safe flight envelope. And of course, there are many other bits of the envelope. You can also have rate boxes or rate envelopes and a bunch of other interesting things that are also important. Okay, so our goal is to do automatic return to envelope and create a function where we essentially push a button on the controls of the aircraft, and the aircraft takes control and brings itself back into its flight envelope. We want robust common sense strategies. We don't want to create weird and wonderful things because they're probably expensive to do, probably expensive to test, probably expensive to certify, and difficult to move between one aircraft and another. So we're going to try to create things that make sense, that are relatively simple as far as we can, but that's not always possible. Through this whole process, if you have this aircraft that departs its flight envelope, you'd better be sure that we also maintain safe structural load factors on the aircraft. That brings another interesting and difficult dimension into the problem. And we need to be able to test this for large transport aircraft in some way, so we'll need some kind of model. And what we're going to be focusing on quickly today is post-stall spin recovery as an example, to give you an idea of how we handle that specific problem. And again, we're going to model, we're going to create a strategy, and we're going to test and validate that specific strategy. So firstly, the model is actually quite a difficult thing to get a hold of. There are very few good high angle of attack and high side slip and high attitude rate or angular rate models out there because it's a very expensive thing to create. And it's usually not necessary because your aircraft aren't supposed to exit their flight envelopes. But there is one good model out there that we decided on, and that is NASA's generic transport model, and NASA gave us permission. Thank you very much, NASA, for using their model. The model is, if you see it in the top right over there, is essentially a twin turbine large transport aircraft scale model that is wind tunnel tested, CFD'd, and tested with system ID in flight, so that we can analyze exactly how that vehicle behaves, or well, NASA saw how it behaved, and created very high angle of attack, very high incidence and flow angle type models with high attitude rates, and also large control deflections under those sorts of conditions to try to understand how those vehicles will behave. So of course, a super nonlinear model, that's awesome. We like super nonlinear things because there are lots of problems in there for us to solve. But at the same time, we need to come up with feasible solutions for industry. All right, so our basic solution approach is to, like I said, be intuitive and robust to various aircraft. We want to base what we do on good piloting practice as a start. So first thing to look at is what good piloting practice looks like. And quite basically, pilots are trained to recover linear aerodynamics first. So reduce rates, angular rates, and get the flow over the aircraft to be within its envelope. And if that's your starting point. If you can do that, then after that you can sort out angles and airspeed and all those other interesting things are important, and altitude, of course. And the interesting thing with large transport aircraft is you have a fly-by-wire system with lots of protection systems inside there to protect your aircraft against overloads on the structure and all sorts of other interesting things. And we want to be able to transition to that fly-by-wire system as quickly as possible. And you can transition there most safely when you are inside your linear aerodynamic envelope, or at least your acceptable flow envelope. Right, so basically that's the strategy. Recover angular rates and aerodynamic envelope, recover attitude, recover overspeed and altitude. That's the basic strategy that our pilots are also taught to handle the problem. And the question is, can we create something that does that? And I can basically show a flow chart doing exactly the same. Enter upset, recover aerodynamic envelope, recover attitude, recover overspeed. And inside the concept of aerodynamic envelope is damp angular rates, capture angle of attack, and capture side slip. And then after that, recover, 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 and there you go along. All right. Now, unfortunately, if you look at something like the GTM, the generic transport model, what we see is something that is indeed very, very nonlinear, highly nonlinear. There are multiple stable and unstable equilibria outside the flight envelope. So this aircraft can end up in some very nasty conditions and stay there if it does exit the envelope. Actuator inputs and initial conditions will, of course, govern how you transition through this space, this highly nonlinear space where you have all these stable and unstable equilibria. And the short story is we need to analyze more to understand it. So this is the step one, recovering the aerodynamics. What do we do there? And enter bifurcation analysis. Bifurcation analysis is the tool we use on this side. We essentially try to first understand what it is that we're dealing with by solving and tracking the equilibria of this nonlinear system for various static control input deflections to see what the possible equilibria are that you can end up in. And then we use the MATLAB Dynamical Systems toolbox created by Etienne Coetzee and others, and there are lots of interesting publications on it. University of Bristol and Etienne from Airbus and Fulton. But as step one, if we're going to use software like this, trying to track these equilibria, we need to first massage this generic transport model into a form that we can pop it into the Dynamical Systems toolbox, and we did that. We steered clear of fly-by-wire because we're typically outside the flight envelope, so we want to stay away from fly-by-wire there for now. We did some analyses with fly-by-wire as well, but for now, let's stay out of that. We vary the static elevator input as a start. So the specific example we're going to look at here will be post-stall spin recovery. So what I'm going to show you, some interesting bifurcation analyses where we essentially trim the aircraft. As soon as the upset occurs, we reduce throttle to 0, and we then analyze at different elevator positions what the equilibria are that this aircraft can end up in, so that we start understanding its behavior. But we've got to be careful. Bifurcation analysis is an equilibrium analysis tool, so we don't have time domain information inside this. You always have to augment what you're doing with transient analysis of some kind, some time domain info. All right, so my first bifurcation diagram of the day. I'll try to keep it as simple as possible, though as many of you might have seen it, and many of you might not have. So generally, what I'm plotting here is just in 2 dimensions. I'm looking at angle of attack on one side here, and I'm looking at static elevator input, and we're solving for the equilibria. We're solving the differential equations essentially describing this aircraft, this very nonlinear system. So you have blue lines. Blue lines are stable equilibria. Dashed red lines are unstable equilibria. So at 0 elevator, you sit over here, and let's say I move to 20 degrees of elevator input. What's going to happen if I keep my elevator at 20 degrees is I'm going to force this aircraft into stall, at a high angle of attack here that is essentially stall. Luckily, at that point, I don't see a whole lot of other stable equilibria for this aircraft, but this is just looking at angle of attack. So it seems like angle of attack at a 20-degree deflection should settle somewhere around the 20-degree mark for this aircraft. And what this says is if I hold my elevator at that position, I will stay at an equilibrium around about 20 degrees. Now that's the equilibrium. That's not the time domain info. There might be some interesting oscillation around that point, some interesting behavior. We'll have to see. What we also see is that a 0 elevator deflection, we have no stable equilibria at the top here, but only one stable equilibria at the bottom, this blue line, and it's around a 5 degree or so angle of attack, which is good. All right, so pretty much what this means, and there's more to it because you can have nasty transitions between these unstable equilibria as well, but pretty much for now, after we've done some analysis on regions of attraction and so on, we can see that if we move our stick back from 20 to 0, the good news is that we're going to recover the angle of attack. All right, that's pretty much what this means for us. And we have to do an analysis like this to figure that out for this kind of aircraft. Not a very high-tech solution, but a very important one. Again, if you listen to David Voss this morning, this is the kind of problem, if a pilot, for example, holds that stick up, that can cause some serious trouble. Okay, and then on roll rate, this is a little bit more insightful. Now, this is all at the same time. Remember, it's the same experiment, finding equilibria. I'm just plotting two-dimensional graphs here because that's what I can display here on the projector. Again, elevator on one side, roll rate on the other side, and what you see is this blue stable equilibrium. Two branches here. So essentially what happens is your aircraft, when you pull up on the stick, it stalls. When it stalls, it either rolls one way or the other way. So if it rolls one way, you're on that branch. If it rolls the other way, you're on this branch. And this is called a spin. So you pull up aircraft, you stall, and the aircraft rolls to one side. It remains at a high angle of attack in stall, and it remains in rotation. That's a spin. So it's quite a nasty thing to be in. Don't worry, this won't happen to you. But if you look at this analysis, then you see it's a possibility in the dynamics of the aircraft. All right, so the point is to try to steer clear of this. But if you have ended up in here, what do you do to get out? And the answer, again, is actually quite simple after this analysis, and that is that if you've done some regions of attraction analysis and you verified that you don't have all sorts of weird behavior jumping between these unstable equilibria at the top and the bottom, it pretty much says that if you just let go of your stick and go back to your trim position, your aircraft will stop rolling and it will come out of stall. All right. So a very simple answer, indeed a very, very simple answer. But simple is good. That's what we're looking for. Now, for some of the other problems, the answers aren't quite as simple. But what I'm illustrating here is the analysis method. So the analysis method, create, find, adapt a high fidelity model, use bifurcation analysis to analyze what the possible modes of behavior would be. And then, of course, the next step would be for us to do some time domain analysis here as well to see what actually happens when we do these things. But remember, this was just step one, aero, rate recovery, aero and rate recovery, aerodynamic flow and rate recovery first. Very simple. Just put your stick back to 0 elevator. Attitude recovery we can do with protected fly-by-wire control. So you can next bring your pitch and roll, say, back to level flight. And at the same time, you can use that protected fly-by-wire system to climb back out to altitude to reduce overspeed that you've picked up and improve your altitude situation as well. All right, of course, you need to open your throttle to do this. So let's see what this looks like in a simulation, time domain simulation. Firstly, there you go on your normal flight. You induce, in this case, we very specifically induce with the elevator a stall and then spin. Aircraft spins at about 6,400 feet. We start at 8,000 feet. We activate our recovery, which is bring back elevator back to 0, use fly-by-wire to recover with the flow chart that you saw there, do attitude recovery, do overspeed recovery done. So you drop about 600 additional feet after you've activated recovery. And in this case, like I said, the specific spin is induced in this model. All right, we force it into the spin. And in the time domain, you see the same thing. There you go. Induction of a high angle of attack. There's angle of attack, there's time, and this is side slip. You see the angle of attack going to about 20 degrees in the time domain, just like we predicted when we looked at the bifurcation analysis. And about 2 to 3 seconds, depending on your situation, you can come out of that spin. Then you recover your attitude, overspeed, and there's a post-recovery phase that we have, and the same holds here for side slip. All right. So that's it. That's the process. That's how we recover this aircraft. But this is just the tip of the iceberg. This is just one way of analyzing the problem and showing what it is that we can't do, quite roughly. And just for the specific problem of post-stall spin recovery, that we can do these sorts of analyses and show that there are some simple techniques and that we can somehow verify with some good simulation and some good tools that these techniques make sense and and should or warrants it, they warrant attention. All right. So I'll click on this video, please. It's slightly accelerated, about 2 times faster than it should be. Aircraft flies along. We induce our nasty spin. They stall, and there we go with the spin. This is what it looks like. So it's quite nasty. You're in a high angle of attack stall all of the time while you are rotating. And then at some point here, elevator back. And remember, it's accelerated, so it looks a bit quick. Then we recover attitude, pitch up to reduce overspeed, and the aircraft levels off again at some safe altitude at the correct speed. All right. So we can see in time simulation that what we have here makes sense, at least when we use this GTM. All righty, that's improving safety. The next part of my discussion, I'll spend about 5 to 10 minutes on this one, is improving efficiency. Improving efficiency, of course, makes sense. We all want to save fuel. We all want to use whatever fuel we do use wisely. We want to be green. And the example that we use here, that we operate on at Stellenbosch University together with University of Cape Town. The University of Cape Town looked at the aerodynamic side of this problem. We overlapped on analysis, and then on the control and simulation and so on, that's where Stellenbosch University takes the lead again. Automated formation flight, that's what we're trying to do. So the FAA says we're going to have about a 66% increase in airliner traffic up to about 2033, so the next 15, 16, 17 years. We are looking at formation flight to try to reduce drag and increase the lift a little bit to have more efficient flight, just like geese or whatever else in a flock would do. So some aircraft at the back getting a fuel savings by doing transcontinental, transoceanic formation flight. All right, that's the general project. Firstly, it's important to notice that these pictures at the top do not represent formation flight. In fact, that's a total misunderstanding that we create with these. This is not supposed to be for formation flight. We really are operating 10, 20, 30 wingspans behind the leader aircraft. We are not popping our wing right next to the leading aircraft. We are 20, 30 wingspans behind, and we mostly control our lateral separation and put our wing or wings inside the persistent trailing vortices that we have during cruise. All right, so you have these vortices coming off the wingtips, and you put your wings somewhere inside there, way behind the aircraft, to try to exploit some drag or drag reduction and lift gain. All right. So again, autonomous formation flight is the plan. We're not talking here about large swarms of things. We're just trying to look at the control of the aircraft and trying to figure out where those aircraft should be and roughly how to push them into the spots where they need to be. Our focus is therefore on dynamics and control. We're going to calculate real fuel savings with some complicated engine models and basically trying to get to practical solutions again. Here we're quite advanced with the modeling and the understanding, and we have some initial results in algorithms and testing that I'll just very quickly share with you. All right. So I thought the interesting thing here is to mainly look at the model and look at some analysis of what we see here. Firstly, again, most of the literature we see is for smaller aircraft trailing, so smaller aircraft right at the back. A UCT study, University of Cape Town study, was on using a Boeing 747 to try to analyze what happens in the wake behind here, and we piggybacked on top of that and joined with University of Cape Town in this project together with Airbus and National Aerospace Centre. So what we basically do is we have a trailing vortex model behind the leader aircraft, and we convert this flow field somehow to new coefficients, or essentially a new model for the trailing aircraft. So you'll have your old aerodynamic coefficients, and you have these delta coefficients that you get from a lookup table or some polynomial fits to get the new aerodynamic coefficients of the aircraft. So the aircraft behavior changes depending on where you are on the flow field. All right. So once we have that, we need to realize that what we're really going to look at now is to look at these C deltas. How do things change based on where you are on the flow field? So here we are around 20 or so wingspans behind the leading aircraft, and we are in a position of looking at lateral separation here, coefficient of drag, the delta coefficient of drag, so the change in drag, change in rolling moment of the aircraft for lateral separation. And we normalize it to 1 wingspan, 2 wingspans, and over here we're at 0 wingspans. Interestingly, if you fly directly behind, you increase gain. It's a positive gain coefficient. You increase your you increase your drag on the aircraft. But there's a spot here around a lateral separation of 0.7 wingspans where you do significantly reduce drag, and that's one of the interesting places we're looking for, and there seems to be some more reductions somewhere along this line here as well. All right. But be very, very careful. This is the rolling moment on the aircraft. Can we trim out this aircraft? Is it possible to trim the aircraft? That's the important thing to consider. So let's look at this from a trim perspective and then from a dynamics perspective. Aileron deflection here at the bottom, lateral separation. So we see here that it would be impossible to trim this aircraft. We would need aileron deflections of 150 degrees theoretically, and we don't have that to trim this aircraft in most of the region behind. There's what we call a sandwich region here in between, where you could possibly trim the aircraft. And then there's an outer region here where you can definitely trim the aircraft. All right, so you can operate somewhere there, you can operate somewhere here around 0.7 wingspans, or about the 1 to 1.3 wingspans separation laterally. Right, but again, you're flying directly behind the same height, you're in the training vortex, but you control your lateral separation. What you see in the throttle setting side is that in both these regions, the sandwich region over here, and when you look at the outer region, you do get throttle savings. That top dashed line is your standard throttle setting in cruise, and this blue line, whenever it goes beneath that, that means you have a throttle setting that's below your standard setting. So inside this area here, in this envelope where you have your sandwich region, you can get significant fuel savings, and you can also get significant fuel savings out here. But you get more inside the sandwich region. All right. Again, then looking at the sandwich region here and the outer region, and we look at it from a dynamics perspective. And if you look at it from a dynamics perspective, you see that how the poles of the system move, and a long story short, but the length of these little black lines tell you how much those poles migrate as you move around inside those zones. And the reality is that inside the sandwich region, it's not a nice place to be. Even for small motions, your dynamics change very, very significantly. While if you're out in the outer region, your dynamics do not change so much. All right, so here you're going to get turbulence, you're going to get moving poles, you're going to have to adapt your control system very carefully. Here you could probably manage with most basic control systems. All right, so many pros and cons. Best drag reduction is somewhere in the sandwich region, and a significant drag reduction in the outer region. All right. On control, I'll talk very quickly about the control side. We basically have our leader aircraft and a follower aircraft. We have a conventional controller for our leader aircraft. We don't mess with it. It flies along. We have a formation hold controller that pretty much just controls the rear aircraft to be in the right position relative to the front aircraft. But the reality is, for us to be able to predict exactly where the sweet spot is going to be, where you're going to minimize your drag and improve your lift, that's no good, because you're probably going to have to converge to it. So there are two parts to this problem. There's a formation hold controller that brings you to the right spot, and there will be the necessity for an extremum seeking controller of some kind to optimize to get you right into that sweet spot. Well, how do you know you're in the sweet spot? Your pitch angle or angle of attack starts changing, it starts reducing, and then you know you're at a spot where you don't need so much angle of attack to keep your aircraft in the right position. Okay? Extremum seeking control, we keep it quite simple. At this point, it's pretty much a con scan, a conical scan type approach, where we search and we use our pitch angle specifically and our angle of attack as inputs to this to decide when we think that we are at the extremum, where we're at our sweet spot for a reduction of drag. All right. And in this case, I can actually, it's worth clicking on the video. There's some weird effect at the back. We can start the video, please. Because our environment, of the land environment that we have in the video, is actually quite constrained. But the only reason I'm showing you this, it's quite a boring video, because now that's for aircraft tracks, the one in the front, is to also show you the separation. It gives you an idea of what we're talking about. There's an aircraft at the back, here's an aircraft at the front. That's really what we're talking about in formation flight. And it's possible for us to already do this. We're now pushing some more results, but I don't have lots of results at this point to show you. But to give you an idea, that we've done analysis, we understand what the situation is, and we're continuing on the control side. All right, so that brings me to the end and my, just about my final slide, this conclusions. What I tried to show you was that we could look at, say, functional automation, at improving safety, improving efficiency, and I showed you some example projects that we're involved in to try to do that, to solve the control challenges that we're dealing with the future aircraft that we're going to be creating for the extra 66% of aircraft between now and 2033 that we'll see in our airspace. But mainly what I want to leave you with is the idea and the concept that we have complicated problems in industry, really complicated problems. There's a lot of insight in industry to these practical problems that we as academics can learn from. And there are many unique constraints to consider. For example, certification, regulation, these sorts of things that we need to look at all of the time. And if we don't look at that right from the start, our solution approach might never be compatible with what industry requires. Then from the academic side, we have access to powerful tools and support networks, so we can be of use to industry to solve some of these problems. And of course, we have the time and the need to solve these difficult problems. It's what we want to do. So there's a good mutual benefit that can be gained from this collaboration. But there's no way that we can have good mutual collaboration if we don't have champions and support. In this case, we're supported by Airbus, the Department of Trade and Industry, and National Aerospace Centre. So my last slide will be to thank a number of people. There are many, many more people involved in our projects and our programs, but the specific projects I showed you here today, a lot of people at Airbus who we work with and who help us and assist us on many, many levels, and the National Aerospace Centre, University of Cape Town, and Stellenbosch University. And there are armies of people who work with these individuals, especially graduate students, researchers, engineers at the different organizations who we have to thank to be able to work on these sorts of projects. Then thank you for listening to me this evening, and have a very good evening.
Okay, it's on behalf of the organizers of the Congress, I would like to thank Professor Jones for your extremely interesting talk on these large aircraft. It seems there are many challenges, modeling challenges, control challenges, and then obviously the implementation of these control laws and the testing, etc. Good you have such partnerships with Airbus. That's fantastic to hear. I think we'll take questions after the session if Professor Jones has some time still, otherwise probably by email, or you can come forward and talk. And yeah, so the session is then ended, and enjoy the rest of your evening. Thank you. Thank you.